One of the really big applications that we get early on when we look at the idea of a derivative, the idea of being able to describe the rate of change of a function, is we can write the equation of a tangent line to the function. We've alluded to this idea of a tangent line a couple of times now throughout the course. Remember, a tangent line is going to be a line that intersects the function at one particular point, and at that point, it has the same rate of change of the function. So let's write the equation of the tangent line to the function y equals 2 square roots of x at x equals 9. So that's the objective here. We're given a function, we're given an x value. We want to write the equation of the tangent line to this function at this point. Well, if I want to write the equation of a line, I need two things. I need its slope, or its rate of change, and that's where the derivative is going to come into play. But I also need a point. So we already know the point, or we can at least find it rather quickly. If I take x equals 9 and I substitute it into this function, I get 2 times the square root of 9, which is 2 times 3, or 6. So I already know the point 9 comma 6 is going to be on my function just by taking x and plugging it in there. And so it shares the point. It's going to share this point with the function. But what we also need is the rate of change of this function y equals 2 square root of x at x equals 9. And that's where this idea of the derivative is going to come into play. So if I want to know the rate of change of y, I'm looking for y prime. And let's build the notation here. It's the limit as h approaches 0. Well, if I take a look, it's going to be f of x plus h minus f of x all over h. And I kind of introduced the function notation here, but I'm kind of using it interchangeably here. If I take a look, f of x plus h is going to simply be, and so let's go ahead and just write it in here. I don't have to do the algebra work like I did on the previous video. Yeah, that's going to come up when we actually evaluate this derivative, or take the derivative. F of x plus h means I'm going to put x plus h in right there. I get 2 times the square root of x plus h right there, minus f of x, which is 2 square roots of x, and it's all over h. Now then, before we get too far into this, and our idea with radicals is going to involve the same trick we learned with radicals when we evaluated limits in Unit 1, I do see one thing that I can do here. I've got a 2 in front of both terms in the numerator, so I can actually factor that 2 out. And remember when we evaluate limits that any scalar multiple can come out in front of the limit statement. So I'm going to do myself a favor. I know that the algebra is about to get a little bit tricky. I'm going to go ahead and factor out that 2 and say that this is 2 times the limit as h approaches 0 of the square root of x plus h minus the square root of x all over h. That's just going to clear up a chance for maybe making a silly algebra mistake down the road. So what I do want to do is I want to see if this will simplify using the conjugate of the numerator. So this is going to be the square root of x plus h. Remember, I'm going to change this minus to a plus. So plus the square root of x all over the square root of x plus h plus the square root of x. And you're going to see some similar things happen to when we evaluated limits involving radicals back in Unit 1. The numerator is going to operate as the difference of squares. So this is equal still to 2 times the limit as h approaches 0. But the square root of x plus h squared is x plus h minus the square root of x squared, which is x. Now then, the denominator, just like in Unit 1, let it be gross for a second. That's going to be h times the square root of x plus h plus the square root of x. Now then, if I take a look at the numerator, x plus h minus x will simplify. That's 2 times the limit as h approaches 0 of, well, the x's are going to cancel, so that's just h over h times the square root of x plus h plus the square root of x. Well, just like when we evaluated limits involving radicals in Unit 1, we now have a cancellation. The h's will cancel, so this is 2 times the limit as h approaches 0 of 1 over the square root of x plus h plus the square root of x. We are now ready to evaluate this with direct substitution. I can substitute 0 in for h, so this is equal to 2 times 1 over the square root of x plus 0 plus the square root of x. That's what I get when I substitute 0 in for h. And now I don't have a problem where 0's in my denominator. In fact, I have the square root of x plus the square root of x, so this is equal to 2 times 1 over 2 square root of x, and the 2's end up actually dividing out for us, so the answer, for the derivative at least, is 1 over the square root of x. So I can say y prime, the rate of change of this function can be expressed as the function 1 over the square root of x. Now then, going back to what we originally started with, writing the equation of a line. We had a point, we need the rate of change at x equals 9. So let's evaluate y prime, and this little vertical line is going to be the notation to say we're evaluating it at x equals 9, is going to be 1 over the square root of 9, or 1/3. So the rate of change at x equals 9, and that's what this right here is saying, the rate of change of y at x equals 9 is 1/3. We already know the point, and so now we can go and plug this into our point slope form of a line, which is y minus y1 equals m times x minus x1. In fact, you'll replace this idea of m with the instantaneous rate of change. So y minus, let's see, my y value for the point was 6, equals the rate of change, 1/3, times x minus the x value, which is 9. And I get y minus 6 equals 1/3 x minus 3. You do want to make sure whenever you're asked to find the equation of a tangent line that you do give it in the form of y equals. So add the 6 over, and you get y equals 1/3 x plus 3. And I would really encourage you to see this graphically. Graph this function y equals 2 square roots of x. Graph this point 9, 6. You will see that this point is on this function. And if you graph this function and you graph this point, and then you graph this line on top of it, what you'll see is that this line goes through the point 9, 6, and it has the exact same rate of change of this function at the point 9, 6. And it's actually a very powerful tool for us moving forward. But this is the process in the future when you see to write the equation of a tangent line. This is the process that you'll go through. You need a point and you need a rate of change. Well, the rate of change is going to be the derivative evaluated at that particular point.